Reading Statesman, we're working on lesson 10.3 using chords, and now we're going to start to relate the lengths around a circle in that are on the circle to the lengths that go through it. I'm going to start first, and of course with your compass, you're going to construct a quick circle here. Let me grab my straight edge, make sure that I can give a good straight line as I create a diameter, right, which is a chord that goes through the center, and put a point that's going to be on the circle to the center, which is of course a radius. And here I have A, B, C, and D. Right. So in my given here, I have circle B, which has a couple different lengths. First of all, AC is going to be equal to 9, that diameter. But there's a central angle that's inscribed here, which is the measure of angle ABD, which is going to be 40 degrees. Okay? And what we're going to find is this arc length of AD. Now, how are we able to do that? Effectively, what we're trying to find is what's the distance of this arc, that curved line, but again, we won't call it a curved line, it's just an arc, it's a portion of the circle from A to D, that minor arc. Well, the way we're going to figure it is the following. It's going to be through a proportion. So, of course, that 40, right, which is ABD, that central angle, 40 degrees, is going to be that much of the entire circle, which is 360. Now, what we can figure out here is we want to find that arc length, right? So this is our arc measure in the numerator. And at the bottom, we're going to take the whole circle, okay? Now, that length that we have, like that distance, we don't know. This is AD. This is what we're looking for, arc AD. However, the length around the entire circle, we do know. We do. We can actually measure all the way around here. Remember what that is called. That's referred to as circumference. The relationship between circumference is the diameter times pi. So we have a diameter, right, which is AC, that's 9. So we're going to say that this guy is 9 pi. From there, we can take a cross product to solve AD. So 9 pi times 40, which is going to give us 360 pi. And that's going to be 360 times arc AD. All right, let's get AD by itself. So we divide by 360 on both sides. And the answer, by the way, so the length of this guy right here is just going to be pi, whatever that rational expression is, a little bit over 3. All right, next. Let's talk about the relationship with a chord to the arc created outside of it. So let's get another diagram here. So draw another circle. Oops, that's an ellipse. Let's go ahead and make a better circle. My software will do a great job. Your compass will do a fabulous job as well. So I'm going to draw here circle E. I'm going to create 2 chords here. One at the top, and then one somewhere down here. Okay. So what I have here is A, B, C, and D in circle E. Now here's what we're about to learn, is the following, that if AB and CD, those chords are congruent, these line segments, right, that connect with endpoints on one end of the circle, that are endpoints that are on the circle, then the arcs opposite them are also going to have the same relationship in the same circle. They will be congruent. So this arc, the length on the circle from C to D, is the same as A to B, or arc AB congruent to arc CD. All right. So let's get a little bit more. I'm going to give you guys another little theorem here. Here we go. The circle. Again, circle E. I'm going to create 2 chords here. One of them through the center, which of course we know that a chord through the center is the diameter. So this is going to be AC. And then I'm going to create another chord here, not through the center, which is going to be BD. Don't worry about this little overlap I made right there. I just don't want to redraw that line. Okay, so here's what we're given. We have circle E. Moreover, that AC, that chord, is a diameter. All right, so here's what we're going to learn here. If I were to say that this here at the point where we're going to say that AC and BD intersect, and we'll call this point F, if this is perpendicular, then the following relationships are going to happen. Then arc BC will be congruent to arc DC. Has to be. And here's going to be why. Moreover, D, F, and BF are going to also be congruent. That segment BF and DF. Now, these aren't entire arcs, right? This would be from here to here that would be congruent, right? So we got learned in our last little tidbit there. What we have here is we're going to say the following is going to be true, right? So if we have this arc and this arc, right? It's going to make that these chords here, DC and BC, are going to be congruent, okay? As long as we're saying that these guys are congruent. And then we have FC, okay? But here's where we're actually going to establish the first set of congruence. It's actually going to be with these two lines right here, and that's where we're going to go with all this. So here's how this works. It winds up being the hypotenuse leg, because if I take DE, this guy right here is a radius, and EB going to be the same. Those will be congruent. I have my right angle at F, and then EF also going to be congruent reflexively. So then I have hypotenuse leg, meaning that I have two congruent triangles, meaning then that DF and BF are going to be congruent. That works. Now that I've established this, right, I have side, I have another angle right here, right, that right angle, and then of course FC reflexively, that side, making here D to C, this hypotenuse that I could construct congruent, right? So these will be congruent, and look at what I have then. I then have chords that have an arc opposite, which of course then make BC and DC congruent. If you didn't really follow all that, you know, I'll probably rewind that and give it another listen. But I effectively just did two proofs as to why this exists. If you don't get it so far, that's not as critical as enforcing this theorem. But again, I'm just not making things up. There's proof as to why these things work. Okay? So, next. Drawing another circle. Let's actually do some problems. And I have circle M. Circle M has this diameter right here. The chord to the center. Then I'm going to have another chord. This is H, J, K, and this is L down here. So here's what's given. These guys are perpendicular. JL, oh, by the way, this is at point N that they intersect. So these are perpendicular. This arc here, JH, is 2x minus 8 degrees. And JK is 127 minus x degrees. These are not central angles, right? These are the arc measurements, okay? And last but not least, I have 14 as my measurement of NK. So first thing we're going to solve for is we're going to solve for KH. All right? Well, remember we had just proved to be true. KH, that's this whole segment here. Well, this is going to be pretty straightforward. If NK is 14, right, that thing shows that HN and NK, when we have that perpendicular relationship between JL and HK, right, between the diameter and then a chord going through that diameter, then boom, we've got a congruent segments, HN and NK, therefore together 14 and 14 is 28. We're now going to find the measure of arc HLK. All right. Well, remember, JH and JK as arcs have to be congruent. They have to be, right? Because this relationship exists. So, because that's the case, then we know 2x minus 8 is going to be equal to 127 minus x. And then we're off to the races with solving an algebraic equation, right? We're going to add x to both sides. So 3x minus 8 is equal to 127 plus 8 plus 8. So 3x is going to be equal to 135. Right? We're going to divide by 3 on both sides. 135 divided by 3 is equal to, according to your calculator, 45. How are we going to use that? Well, remember what we have here. We know that JK, arc JK, is equal to 127, right, minus x, which we're going to plug in here, 45. So we know arc JK is equal to 82, okay? Well, then, how do we find HLK? Well, we can figure out HK, right? HK, since JK is 82 of it, then we know that HK is going to be equal to 164, right? It's just double it. It's still a minor arc, less than 180. So then to find HLK, we're going to take 360 and we're going to back it out. And we're going to subtract HK, and that's how we're going to get arc HLK, which is what we're looking for all along. So 360 minus 164, and that's going to be equal to 196, and that is arc HLK. And that's your answer. All of that work required in order to solve this problem. Okay, so make sure you show your work as we do this, of course, as always. Next, we have 1, 2, 3 more examples. So, next, here we go. Circle D. This one should go quick. We have A, B, C. Then we're going to learn about this type of angle in the next lesson, but for now we don't really have any other guidance, except for that we're given here is that AB and BC are both equal to 9. So we have circle D is our given. And circle D, the question is if we have the measure of arc AC, which is a minor arc equal to 150, then how much is the measure of arc AB equal to? Not segment, arc. And how do we do it? Well, we do the following. Remember, if this and this are congruent, these two chords, AB and BC, it means these arcs opposite them are also going to be congruent. Okay? So AB, arc AB congruent to arc BC. Okay? And we know that 360 minus AC, okay, is going to give us the measure of arc ABC. and we have AC, which is 150. So that's going to give us 210, okay? And that's going to be the measure of arc ABC, right? Now remember, AB and BC are the two parts that make up ABC. Therefore, we just have to half this guy. So 210 divided by 2. This is going to be 105 degrees, and that is your answer. That is the measure of arc ABC. Sorry, we only have one more example, but I have another theorem to give you guys here. So it wasn't an example, or just another thing for us to learn here. Show you guys here. Okay, so here's our circle. Of course, we got a center. And this is circle E. Okay. We got two chords. All right. And draw them where they're congruent, but I'm going to have to prove that to be so. So I have A, B, C, and D. And here's what we're going to be given, is that we're going to have E is going to go perpendicularly to F, at chord AB at point F. Same thing, E is going to move perpendicularly. It's going to be drawn perpendicularly. We're going to connect from the center E to this point G. Now, EF and EG are not segments that are on the same diameter line or whatever. But we're going to be given that EF and EG want to be congruent. And this is only going to be the case when we have the following. If AB is congruent to CD, that's going to happen if and only if IFF, we have EF also congruent to EG. Okay? So that this and this are congruent as long as this and this are congruent. They're the same distance away. How do we prove it? Gentlemen, it's pretty straightforward. It's through that, right? It's going to be through hypotenuse leg, effectively, each time that we're going to have those congruent triangles with us, okay? I also could start to use angle side as well. So, last part, last example. Almost in 10.3. Another one of my fantastic geometry videos that I know you guys really look forward to watching, especially just in your free time all by yourselves. I have E again. I'm going to draw this guy a little bit closer this time. All right. I have two other little segments to draw here. And of course, these segments here, this chord AB and CD, are not drawn to be parallel, okay? I have point P and point Q, okay? So again, I have circle E is given. We have EP and EQ, and they're equal to 12, okay? Moreover, CD is equal to 5x plus 7. I have AB, which is equal to 7x minus 3. And we're going to find the radius and circumference of circle E. Also, I have one more distance here, which is 16 right there. All right. Well, let's mark the diagram. You know, this is 12, and this is 12. Oh, also, if these guys are equidistant, what do we know? We'll have this perpendicular relationship right here too. Okay? So, we know that AB and CD are going to be congruent chords. Why? They're both equidistant from center. That's what we just were given in that last if and only if biconditional statement. Up above, this right here. Okay? So, let's do some math. All right? Also, we had BP, sorry, A, B, and C, D, right? So AB, which was 7x minus 3. So I'm gonna mark my diagram just so I can do this a little bit better. And then this guy, CD, 5x plus 7. All right, well, I know that those are congruent, so I can actually start to operate here. 7x minus 3 is equal to 5x plus 7. Okay, this should be pretty straightforward. So we can solve this and get a value for x, and then we can get a value for A, B, and C, D, okay? Of how I even got this 16. Sorry, this 16 wasn't given here. But this will wind up being 16, gentlemen. I'm sorry. I'll show you how we get it. So we have 7x. Sorry, this was from when I previously did these notes. Is equal to 5x plus 10, and I'm subtracting 5x. It's me marking up the diagram. That's why I got that 16 in there. Ay, yikes. Here we go. That was almost bad. 2x is equal to 10, so x is going to be equal to 5. Right? And again, since x is equal to 5, we're going to take this guy, and we're going to plug it back in, right? Because we know that AB is equal to 7x minus 3, or 7 times 5 minus 3, which is going to be equal to 32, right? And we know that AP is equal to BP through the theorem that we had, right? Because PE is perpendicular to AB. Okay? Therefore, to get BP, we're going to say that it is just half of 32, which is going to be equal to 16. So that's how we got this 16 back up here. It wasn't just randomly made up by me. But that's how we were able to deduce that. So now that we have that 16, we want to find the radius, right? Well, gentlemen, if this is 12, look at BE. BE will be our radius right there, right? So we can say that PE squared, right, plus BP squared is equal to BE squared. The Pythagorean theorem, right? PE we already have. That's 12, so we'll know that 12 squared plus 16 squared is equal to BE, which is that radius, the thing up here that we're trying to solve for, squared, okay? 12 squared is 144, plus 16 squared is 256. That's r squared. 144 plus 256 is 400. So we solve for r, right? We're going to take a square root of both sides. So 20 will be your radius. Excellent. And of course, to find your circumference is equal to pi times your diameter. Remember that diameter is equal to 2 times the radius. In other words, the circumference is equal to pi times 2 times the radius, or 2 times pi times r, 2 pi r, right? But 2 times the radius, your circumference is equal to 2 times 20, which is 40 pi. And that is your answer. So you guys have your instruction. You guys can move forward and complete lesson 10.3. If you have any questions, come see me during office hours.